Right, so for the physical properties of all these carboxylic acid derivatives, as always, we look for the types of intermolecular forces present in these molecules. So what are the intermolecular forces? You all know them at this point. There's van der Waals forces, it's the weakest type, dipole-dipole forces, and C, H bonding. So those are the types of intermolecular forces. So assign those types of forces to all these different molecules and then come back to us. So you've paused it, you've done that, you're back. So all of the molecules are polar. All molecules have van der Waals forces. So all of them are going to have A and B. Which ones have hydrogen bonding? For hydrogen bonding, you have to have an OH, NH, or FH bond. So that would be these two. We have an OH there, we have an NH there. So these three don't have H bonding. These three would have A and B, whereas these two would have A/B/C. So if we're thinking about boiling point of all these different molecule types, what are going to have the higher boiling points? And you have a higher boiling point if you have more intermolecular forces. So these would have the highest boiling points, and these would be harder to predict. All of these molecules have similar molecular weights. This is the highest at 78, and the lowest of any of them is 72. So all between 72 and 78. What are the boiling points? So these ones that only have the same types of intermolecular forces are 52 degrees Celsius, 58 degrees Celsius, and 80 degrees Celsius. So a little bit of a swing there. But once we get the ability to hydrogen bond, we really see those values go up. 142 degrees Celsius for this alcohol, or for this carboxylic acid, and 213 degrees Celsius for the amide. So the intermolecular force types really do matter. So why would the amide be so much of a higher boiling point compared to the carboxylic acid, despite having all the same types of intermolecular forces? Well, what's the strongest type of intermolecular force? That's the H bonding. And which of them can do more of that? Well, the amides have, in this case, there's an NH2, so those are two H's that it can kind of donate in these hydrogen bonding. So amides have more, we'll say O/N H bonds. So either O or N to H bonds. So that gives it more H bonding potential, POT potential. So that increased H bonding potential leads to more intermolecular forces, which means it is going to have a higher boiling point, higher melting point, etc. So that's what we know about all these different types of molecules. And in retrospect, it's in our course packet, so I put it in there, but I don't really know why I included the ketone here. This isn't technically a carboxylic acid derivative. All of these ones are. All of them have the carbonyl, and then they have another polar atom that is attached to that same. So all this one, they're all in the same oxidation state, whereas the ketone isn't as oxidized of a functional group. So we're going to talk about the reactivities of these types of carboxylic acid derivatives right after I rearrange the board. These carboxylic acid derivatives generally react. Well, would we expect them to be electrophiles or nucleophiles? Well, all the way back in chapter 20, now we've done chapter 20, chapter 21, now we're to chapter 22. We've always seen them react the same way. There's a large partial positive on that carbonyl carbon, and electrophiles are positively charged. So these are active as electrophiles. So electrophiles, I'm just going to write E plus here. Electrophiles react with nucleophiles. So how are those going to occur? And really, we've seen this type of reaction to some degree in chapter 20 when we were reacting esters, amides, and carboxylic acids with our reducing agents or our organometallic reagents. But essentially, we would see the nucleophile add to that carbonyl carbon. The electrons would go up to that oxygen. That would give us this intermediate, and we had a special name for this intermediate. We called it our tetrahedral intermediate. Why was that important? Essentially, the tetrahedral intermediate forms, and then the electrons are going to collapse back down, and whatever is the better leaving group is going to be what leaves at this point. We saw that with the like if we added an organolithiate to an ester, this nucleophile would be a carbon, and this Z would be O whatever if it was an ester. The nucleophile adds in. If that's the stronger bond, then when this reforms that double bond, it's going to kick out the better leaving group. And in this case, the better leaving group is this Z group in this kind of general reaction scheme. And that provides, in this chapter, a new carboxylic acid derivative plus that leaving group. And Grignards and organolithiates were such strong nucleophiles that they added to that carboxylic acid derivative, and then they would add again. But in this chapter, what we're going to be doing with these is learning how to change from one carboxylic acid derivative into another. So maybe we start with a carboxylic acid, but we actually want to make maybe an acid chloride. How do we do that? What if we want to go to the amide? What if we want to go to the ester? What reaction conditions will allow us to do that? And pretty much the standard reaction that we're going to see for all of that occurring is this type of reaction where the nucleophile adds, we form this tetrahedral intermediate, collapses back down to our new carboxylic acid derivative and that leaving group. And we call this reaction in general nucleophilic acyl, because this is an acyl group here. This is an acyl group, nucleophilic acyl. And then what did we do? Well, we substituted a nucleophile for a leaving group, so substitution. Nucleophilic acyl substitution. And I already kind of said this, but on your course packet it says this chapter focuses on teaching us how to make any particular carboxylic acid derivative starting with any other derivative. So no matter what we start with, we will be able to get to the other ones. And we're going to talk about this extensively on the next page, but what we want to be thinking about is, well, which of these carboxylic acid derivatives is the most electrophilic? And when I do this in person, I usually kind of prime you guys for the next page by having you discuss this in groups or with your direct neighbors for a quick moment, and then we do a clicker question on this. So it would be a good idea for you to take a minute and think about that question. Which of these is the most electrophilic? If it's most electrophilic, that means it's going to be most reactive, and that means if it's the most reactive, it's going to react fastest. So the least electrophilic is going to be the most stable. Most electrophilic is going to be most reactive. So more on that soon.